Okay. So we are recording. If I'm not audible, please stop me in between. Anytime the audio goes away, I am having some issues with my headphone. Okay, great. So all this while we have been we learned bandits and we have done a lot of probability, and we did Markov chains last time. Markov chains was done last time. Recall Markov chains, where we said that the probability of st given st minus 1 dot 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 s0 is the same as the probability of st given st minus 1. This was what we discussed last time. But now we'll try to build on this and build our first reinforcement learning proper model. Before all this, we were doing just action value models. Anyone who remembers what model that we discussed, how many states were there and so on?
There was only
Anyone who?
one state, so the
Yeah,
our Q value was based only upon action A.
yeah. Q only depended on the action, right? So here the Q only depended on the action. So it was an action to real numbers. Am I audible? I think there was a, yeah, you can hear me, right? So action value models or bandits, we saw two type of bandits. One was using gradient descent or gradient ascent, and the other was Monte Carlo sampling. Can you hear me? Just
Yes.
okay. So these were the things that we saw, but it had only one state, and the action determined the reward. So it's like pulling one. It's like a lottery, or you in a casino where you try to pull up levers to see how much prize you get. But you are actually not interacting with the environment itself is not changing. The environment sort of remains same based on your actions. The environment does not generally update itself. Uh, so you just have to learn the values of the actions, not the pair of actions and states. So what is all this will be clear now when we go about discussing each of these components of a reinforcement learning algorithm. So as you recall, so this was the diagram I showed you in the previous class. So this will be the notation that I'll be using throughout the rest of the course is that ST is the state at time t, AT is the action taken at time t, RT plus 1 reward received on taking action t, AT, and ST plus 1 is the next state. So this is the notation that I'll be using. So I've written it down here in a fair, so you can look at that. So basically you will get a sequence like this. You will get, say, state 0, you take an action A0, you get a reward R1, go to state 1. And again, is A1, you get a reward R1, or rather R2, and you go to S2. This continues. So basically it's something like this. So look at this diagram over here. So this agent, the agent over here, takes an action AT. The current state of the environment is ST, and based on the action, based on AT, it shifts to ST plus 1. And what does it return? It returns a reward to the end agent, which is RT plus 1. So this is the broad idea of a reinforcement learning algorithm. So some books also mention it this way, where you have an agent and you have an environment. These are the two interacting parties in any reinforcement learning algorithm. So what happens is that at first, the environment gives you a state st. You observe the environment. This is step one. After you observe the environment, you take an action that is on the environment, at. This is number two. And then finally, the environment gives you a reward, rt plus 1. And this is number three. And then fourth is it again iterates to st plus 1. This is repeat. So this is what the broad idea of a reinforcement learning algorithm looks like. So every time you take an action, the environment changes its state, it gives you a reward. And based on that reward, we have to do a lot of stuff. We'll see how to do that. So the sequence here is S0, S1, as I was saying. So this sequence is going to happen. So now so all this sequence of rewards and states are meaningless unless we know. So what is our goal? Our overarching goal is, the overarching goal of RL is called control. So people in electrical engineering, they do a lot of control theory. So control is obtaining the best strategy. Obtaining best strategy to deal with an environment. This is your main objective of an RL algorithm or any algorithm related to biological systems where you want to maximize rewards. So how will maximize rewards is going to be the rest of the discussions. So the sequence is clear to us. Now, as we defined last time, there exists a policy. So this control comes from the policy. The policy pi, say a policy pi, is defined as a mapping from states to a probability distribution on actions. So what does this actually mean? So you have a set of states and then for the policy will map it to a probability distribution. So it's something like this. So you can consider this as a conditional probability. Given a state, this will give you a distribution, right? So given the state S, so say A1, this is pi of A2, A3. So this is say 60% probability. This is 20%, this is 30%. And so this is 10%. Right? Everybody clear? In any case, if you have deterministic policies, one of them would just be 100%. 100% if deterministic. So if you consider a random policy, it encompasses deterministic policies as well. So we'll not discuss them separately, but treat them as a singular or a single idea. So this is the idea of a policy, that given a state of the environment, what is the action you want to choose? So that is called a policy. Next, we have understood what is a policy. Now, what is the reward that the environment gives you is also based on a probability distribution. So say let P be the probability distribution, mapping from states and actions to a probability distribution R. Right? So it's again like for every state, say this is a state, and this is say state 1, state 2, state 3, and action 1, action 2, action k. So for every element in this matrix, there will be a value. So you can plot the heat map, say these actions are more likely to be taken. Right? So this is like, the idea here is, again, it's a conditional probability again. What is the probability of a reward, Ri, given state I and action I? So given the state and action, see, I have the rows and the columns and actions and reactions and states. What is the probability? So this is probability of this is S3 and this is S4. So probability of reward given the action state S2 and action AK. Okay, or S3 in this case, I guess. Yeah. So here, this box again could be a distribution over all possible rewards. So this box here could be, say you can have reward 1, reward 2, and they say there are M type of rewards. Again, it will be a distribution, 60%, say 1%, and so on. So this is what it means. So again, just trying to revise conditional probability with all of you. So this is what the two distributions are. So we learned what is a policy, and we learned what is the reward distribution of the environment. Okay, any questions? So we'll be using these two things to obtain the best or some policy, some map. Before we go on to formalism, is this clear to everybody?
Sir, what is the range of policy? Means SI to
SI to the probability distribution over actions. So it's a map. It's not a function, right? So it will give you a function. Yeah. So it will give you a probability distribution. So from every state, it will give you what is a probability distribution of taking an action, right? Clear, Outreach?
Yes.
Okay. So reward is clear. Reward is also the same. Reward is also a mapping from, the reward function is also a mapping from state comma action to a probability distribution over rewards. Is that clear? Here R is the reward. Right? Very similar. There's no difference, not a lot of difference between these two. So now since we did Markov processes, Markov chains last time, we'll come to what is how we formalize an RL problem to be using finite Markov decision processes. And we'll try to understand. It's also called a dynamic program, stochastic dynamic program, but so famously known as a finite Markov decision process. So let's try to understand what this actually means. So first of all, you don't even need to see, you can see the definition later on. I'll just not write here so that you are not distracted. I'll just write it at the end. Yeah. So let us understand what is an MDP. So you can look at the notes later on, but the idea here is very simple. So what are the components of a RL algorithm? So you agree that there is a state ST, you take an action AT, you get a reward RT plus 1, and you go to a state ST plus 1, right? I think it is a bit. Okay. Can you see my screen? Okay, yeah, now it's here. Okay. So this is the general framework. Again, from ST plus 1, you will take an action AT plus 1. You'll get a reward RT plus 2, and you will go to ST plus 2. So what are the major components of this algorithm? So MDP is defined as a 4 tuple. What are the 4 tuples? What are the building blocks of an RL algorithm we discussed? First of all is states, S. So a set of states. So remember last time we had said that a random process was just a random process was a map from, it was a collection of random variables xi's, say I equal to 1 to t, and xi, each of them were a map from the sample space to the, I don't know why my tab is hanging a bit, but please stay on board. Okay. Okay. So this is, we discussed last time, the random process xi is a map from I to t, and xi is a map, each of them is a map from the sample space to the state space. So this is the same state space. Say state space A, and action space. This is the action space. Then you have a reward. And what else do you have? You have a probability distribution P. We'll see what this probability distribution P is. So this P unifies or defines the distributions over states and actions. Okay, so it's a 4-tuple. So 4 elements completely define an MDP, that is a set of states, actions, rewards, and a probability distribution P, which will come to what is that probability distribution that is linking states, actions, and rewards. So let's see what's the next plan. Okay, great. State, action, reward, and then the probability distribution. Okay, fine. So once we've understood what MDPs are, like what are the components of MDP? So again, what is the principal building block of the Markov chain? What is the finite Markov decision process? This is the word Markov, right? The word Markov is the primary characteristics of this process. Again, what is a Markov property? People, do you remember? We discussed last time.
That the n plus 1 state depends only on the nth state.
Good. So we had seen it last time that the n plus 1 state depends only on the previous state. Good. So which is there on. Okay, again, my tab. Okay, here it is. So that the tth step depends only on the t minus 1th step if it is given to you. Otherwise, it will depend on the closest past, whatever. Now, so let us define a history term. This is called history. This set would be the state of random variables st, action at, rt, st minus 1, at minus 1, rt minus 1, dot, 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 till s0, a0. Fine. So this says that the probability distribution of st plus 1 and say the reward rt plus 1 given the history ft, right, is just dependent on st plus 1, rt plus 1 is just dependent on st and at. Fine. This is what the probability distribution tells you. Any question? So you're given this entire set of history, the history of events that happened to you, only the previous state and action, only previous state and action determines the next state and reward. Okay, so people who are joining late, for them a quick recap. We are trying to discuss what is an MDP, a Markov decision process. It's a 4-tuple of states, actions, rewards, and a probability distribution. And that probability distribution is defined such that given the entire history of rewards, actions, and states, the next state and reward only depends on the previous state and action. So that's the overarching idea of a Markov decision process. That the next state and action only depends on the state and action of the previous state and action. Previous state and action determines the next state and reward. Any questions so far? So this is the probability distribution of the MDP. So it's a this is the distribution I'll be using throughout. St plus 1, rt plus 1 given st and a. This is what I'll be using. Okay. Any questions? Fine. So let's start with some exercises. Just warm up. Okay. So the first question is, what is the probability that the next state is some s dash, given that the previous step is s and the action taken is a? So it's saying that s, you take an action a. What is the probability that the next state is S prime. So how do we find this? This is the first question, right? So we have to find it in terms of the probability distribution P given to us in the MDP. So P is given to us as our MDP definition itself. So how do we find it? Any idea? So probability of ST plus 1 equal to S prime given ST equal to S, comma AT equal to A. What do I have to change it to get this form of the MDP that is there given to us? Law of total probability, what can I write? Can I write this is same as ST plus 1 is equal to S prime, RT plus 1 is equal to R, rewards over all possible rewards, ST plus S, AT equal to A. Yes or no?
Yes.
Okay. In the so as a shorthand, what I'll try to do is I'll write this as R and I'll write this as S prime R S A. I will not write ST plus 1 and ST every time in case it's just to save some time and energy. Okay, so this is the first question we solved. Good. Next, since I've given you one of them, can you tell me ST plus 1 given S prime is equal to S prime such that ST equal to S? So this is the, like we did last time, is the transition probability, right? Yes or no? Transition probability. So this is from S to S prime. What is the probability? This is what we want to try to find using the MDP. Can you tell me how to do that? Using the same MDP definition. Again, what do I need to introduce first? Is the first that question you have to ask. For me, ST plus 1 is given, ST is given. How is the MDP defined? ST plus 1, ST, AT, and reward, right? So what will I do first?
First, partition over action.
Okay. We can partition over both actions and rewards because of what I want again. People who are not following. So we want actions and rewards, which is not here. You can clearly see I don't have an access to actions and rewards. Yeah, tell me, Antariksh.
I said let's partition first over action.
Yeah, you can do that, but I'll just do it in one less step and I'll take a double summation. Is that fine? This is also fine, right? If I take a double summation over all rewards and actions, this is also fine.
Yes.
So I just introduce the two remaining random variables and just use law of total probability. So whenever, this is the trick, whenever you have to use some other distribution which has multiple random variables to get that, to introduce it, just use law of total probability. Just sum over all the other, like use the partition as Antariksh was saying, partition based on other random variables. That is the required ones. Fine. So now what do I do? So now I have to convert it into such that the action goes to the conditioning variable and the rest remains, right? So what will I do? So let's try. So probability of ST plus 1 equal to S prime. Then we can write it. I'll use the definition of the definition of conditional probability, and ST equal to S. I'll just do it once totally, and then I'll show you a trick how to do it faster. A. Okay. So now what do I have to condition on? I have to condition on AT and ST. So I'll do that. I'll multiply and divide by AT equal to A, ST equal to S, AT equal to A, ST equal to S. So once I do that, I can use these two. I can use these two as one and these two as one. So what do I get? I get actions, rewards, or you can rewrite this. S prime A given S and or S prime R A pi of A given S. Any questions? Yes or no? So here, what did I just ran over one step, that is AT by AT comma ST given S by probability of ST equal to S is equal to just pi of A given S. So you can think of it as P of A given S, but we have defined that as pi. So I'll just rewrite the variable name. Is that fine with everyone? Okay. So this is your transition probability from S to S prime. Any questions? Okay. So the idea here is, so the trick that I'll tell you is this. Say you have a probability distribution A comma B given C. To convert it, say you want to convert it into probability of A given B comma C, all you have to do is normally multiply say you have A comma B. What do you have to multiply to get this back? You have to multiply B, probability of B, yes or no? So I'm trying to show you a faster process. Okay. So this is your conditional probability definition, right? So what will I do is, so when I condition B, now bring it to the conditioning variable, you remember that there is this C already present here. So C is already given to me. So what I have to do is, instead of multiplying B directly, you will have to multiply the conditional of B. So that's the intuition to remember. So whatever was on the conditioning variable will just go to the conditioning over here. Just the same equation. Here there was nothing, so there was no conditioning, given nothing. Okay, clear to everyone? Is it, you'll remember this?
Yeah.
I think this will speed up stuff very, very much when you do complicated calculations. Okay, so this too also we did. Now let's try to understand some interesting questions. For example, now we are slowly getting into rewards. So how do we deal with rewards? All this while I was dealing with transition probabilities. So the first thing I'll do today is, what is state and action? What does this mean? So this is the expected reward. Expected reward. And this is a two argument function. What does this mean? And we have to find the value of this function. So again, S means current state, action means current action. Fine. So this is defined as the expected reward, right? That is expected reward RT plus 1 given ST equal to S, AT equal to A. Is this fine? That's all we are trying to say. So this is a random variable of S comma A, right? So it should be a random variable of, as you recall, conditional expectation is a random variable of the conditioning variables, right? You can clearly see S and A is given to me. Therefore, it's a function of S and A. Fine. So so basically what is it saying? What reward to expect if current state is S and action taken is A. Fine with everybody? So now how can I write this as? How can I simplify this? Any idea? I want to write this in terms of the probability distributions that I have defined the MDP on. Am I audible? So first tell me what
We
is,
should add over the end states.
so first let me use Lotus. No, can't I use Lotus to find this? So RT plus 1 is equal to R given ST equal to S, AT equal to A. So this is just the definition of conditional probability expectation. Yes or no? Fine. This is the expected value. Then, as you're saying, partition over S, right? You said partition over the states ST plus 1, correct?
Yes.
So now I'll just partition S in all the states. So I will write probability of RT plus 1 is equal to R, ST plus 1 is equal to S prime given S, T and A. T, I'll write it fast. So what will this become? Pass sum over S comma reward, states and actions, S prime and reward, R, P of S prime R, S A. Clear to everyone? Okay. This is any questions? You can stop me, but I think this is clear. So now let's understand the 3-step. So now you see there is still a variation, right? There could be a difference in reward and there could be a difference in the next state. So now I tell you that I'm giving you ST, I'm giving you AT, and I'm also giving you ST plus 1. But I want to know what is the reward you are expecting. So this is the 3-step reward function. So we'll be using this in various cases based on your implementation. You'll be using either of these. So, but that's why it's important to know the relationship. These are not to be remembered. This is every time you come to a problem statement, you must be able to derive it. You must know that the definition of the MDP is given by this 4th tuple of S prime, R, S, and A. And then you should be able to derive all of these functions by yourself. That's why that's the reason of this exercise. So again, now if I tell you by similar logic, can anyone tell me what would be this 3-step reward function? How will I define this? So it's a 3-step reward. How will I define this in terms of expectation? So it's the expected reward when state is equal to S, AT equal to A, and ST plus 1 is equal to S prime. Okay. Can you tell me? How will you define this first? Just the expect. I'm telling you the definition. Write it mathematically. How do you write it mathematically? Expected value of RT plus 1 given
ST equals to
expected.
S, AT equals to A, and ST plus 1 equal to S prime.
Good. Okay, nice. So ST, AT equal to A and ST plus 1 is equal to S prime. Good. So now what do I do? Now again, I have to bring it to the same form as we discussed in the previous, because we only have access to this function over here on the top. So let's try to do that. Again, summation over all rewards. The probability of RT plus 1 is equal to R given S, A, and S prime. I'll just write shorthand now and R. Fine. So this is what our reward function is. So now I have to, so everything is given to us. All I need to do is just rearrange these terms and I'll get my reward. I get it in terms of the previous form. So how do I do that? I just use the conditional probability definition and Bayes rule. R S A S prime by probability of S A S prime. Now, as I want S and A in the denominator, I will just multiply and divide by probability of S comma A, probability of S comma A. So now I'll take this. This will become the R in R reward, the probability of S prime comma R given S comma A divided by probability of S prime given. So I'm just taking this to the denominator S comma A. This is what I'll get. Fine. Okay. Good. So, but still, again, in the denominator, I don't have access to this function. What do I have to do? I have to write this as, can you tell me? How can I write the denominator in terms of the single probability distribution given to me? What will I sum over?
Reward.
Good. Just divide by the reward. Sum over all the rewards, S prime R, S A. So this is basically a weighted average of the rewards. Fine. Any questions so far? Now we'll go to an example if there are no questions. Okay. So this is taken from the book Sarton and Barto, as which we are sort of referring to in the beginning half of the course. And they are very famous names in reinforcement learning. You can have a look at the book. Richard Sutton is the first author. Fine. So the idea in this question is trying to make you understand what or visualize how an MDP looks like. So what are trying to do over here is we are trying to train a robot to clean a workspace, right? So what does that mean? Say you have a robot. I'll just put two antennas and make this the box. You have a robot, and what it has to do is it has to clean your workspace. Say you have a juice cans, it has to go and pick it up, right? This is all the work that it has to do. Now, what it says is, say you have to collect a can by either going around, that is search actively around the office. You may have to wait. And since it's a mobile robot, it will have a battery life, or you may have to go to recharge. These are the three possible decisions you will have to take, right? The robot has to take one of these three decisions. That is whether it searches, waits, or recharges. Fine. What is given to you? It's given to you that the robot can be in two states, right? One state is high battery, other state is low battery. Now, for every state, there can be set of actions, right? So for high, the two actions are states and you search and wait. For low, it can be search, wait, or recharge, because it doesn't make sense to recharge when it's already high. So you will recharge, consider recharging when your battery is only low. And it's given that the reward is R search for searching, R wait for waiting. Any arbitrary things can happen. And it has been also given to you that assume that the battery reduces with the probability alpha and beta when in high or low state respectively. That is, if it is in high state, it will go to probability with alpha, it will go to a low state, and if it is in a low state, it will go to out of battery with probability beta. Any questions so far regarding the problem statement? Okay. And another assumption you take is waiting does not decrease the battery life of the robot. So you are told to construct an MDP. Okay. You have to construct an MDP to talk about this, to describe this statement. So first of all, what are the two states, everyone? Given to us. So MDP, any Markov process or Markov chain is defined on the states. So first I will draw the states. So which are the states here? Markov chain.
High and low.
Good. Depends on state only. So it's high, say low and say high. Okay. So fine. The two states are done. So now they say that there are a few actions that you can select from. So you can select. So remember again the sequence. What is the sequence of events? ST, AT, RT plus 1 and ST plus 1. So this is a loop and you loop back. This is a RL loop, right? So let's try to understand. So if you are in a low state at ST, say you are in ST at low state, what are the actions you can take? Say ST equal to low. What are the possible actions? Actions in ST? Can anyone tell
Wait
me? It
for
is either of search, wait, or recharge. Yes or no? Correct? Okay. So let's see what happens if you recharge. So if you recharge, say I take an action, recharge. This is how people show it in the. So okay, it's not even. This is also not there. Fine, just give me a moment. It's not appearing on the screen. Okay, sorry for the bad network here at IIC. Okay. So you recharge, then which state are you likely to go? Or will you go? You go to the high state, yes or no? If you recharge from low battery, you will go to high battery. That's the idea. Say with probability 1, you go to high battery. So this is, I will represent, so since reward, this is RT plus 1, and this is ST plus 1, right? The probability with which you go to ST plus 1. The probability P. Fine. Okay. And what is the reward? Say reward is 0. We are not going to get any reward for charging. No reward for charging. Okay. Now give me one more action in the low state. Say you are waiting in the low state. So what are the possibilities if you are waiting? Can anyone tell me? So wait. If you are waiting, what will happen? No one. So say it is given in the question that if you wait, your battery life does not go down, right? Waiting does not decrease the battery life, right? And what reward do you get for waiting? You get a reward of R wait. So okay, so with probability 1, I stay in the low state. Yes or no? So R wait and probability 1, I stay in the. Fine with everyone? So this dot represents what action I'm taking and then what is happening. Fine. So anyone? Any questions? Fine. So next is I search. If I search, there are 3 actions I can take. So with probability, what is the probability that I don't decrease in charge? Can anyone tell me? Stay in low. What is the probability of staying back in low?
1 minus beta.
Yes, low to no is probability beta. So probability low to low is probability 1 minus beta. So this is just 1 minus beta. So I search with probability 1 minus beta and I get a reward of R search. Fine. So now with the rest beta, what will happen? Can you tell me? What will happen? Any ideas? This is the most interesting part of this problem. There will be a beta, right? So you have taken here. Go ahead.
Yeah, so there, when you first defined the question, I was thinking, why isn't there a state no?
You are thinking
But
that what will happen if there is no charge, right?
like, why isn't in no in the state space? And because we haven't even defined the action for the no state space,
Correct.
uh,
So
so I
this,
don't know how to represent.
so no would be no actually means someone has to go and charge the robot. It has to be picked up by the person, as we pick it up and go and plug it in by a human being. So it will go to high state with probability beta, but we will give it a very, very high negative reward, a penalty, our penalty, because we don't want it to be dependent on humans, right? Fine with all of you? I got. So penalty will be high, a high negative penalty. Again, my screen has frozen, sorry. Are you able to see the MDP? Okay, now you can see, I guess. Okay, with a high penalty, I will go to state high. So now similarly, I will draw out the states and actions for search for high. So high, what are the actions possible? If you wait, what will happen? You stay with probability. If you wait, you are here with probability 1. And you get reward R wait and probability 1. I'll just go over it quickly. Again, with probability 1 minus alpha, R search. If you search and you go to the previous state with probability of alpha with R search. Fine with everyone? Fine. Any questions? Anyone? Okay, I'll wait for a moment. Okay. So this is also done. So now this was a very heuristic. Okay, one thing I forgot to ask you is, if I told you to give a design choice, which reward would you give higher rewards? Can you tell me? The rewards have to be defined by the person who is designing the algorithm. So what would be the reward function you will choose? What will be the relation between R wait and R search? Can you tell me? Any relation, any inequality?
Our search should be greater than our rate.
Yeah, R search will be putting it to be greater than R wait, so that we incentivize robot to go around. And also R penalty should be very, very high. That is, once you commit a mistake, serious mistake, this penalty will be so high that you will be careful from the next time to go out of charge. So you will accordingly go and charge yourself. Okay. So we have constructed the MDP. So now let's try to understand a general case of MDPs in general in the field. So all this while we understood states, actions, rewards, and so on. But what is the goal of RL? Again, remind me, what is the goal? Maximize long-term reward or objective. Yes or no? So if you want to maximize the long-term reward or objective, so that's the function that I'll need to choose. So at a time t, say at st, what is the reward you are likely to receive? So that is what we are trying to model over here. So that is called the long-term goal, g of t, or the return function, whatever you try to name it, the gain function at a time t. So what does it look like? So it looks like that at s, say you have st, you take an action at, you get a reward rt plus 1, you go to st plus 1. Similarly, you have rt plus 2, dot, dot, dot. Say you stop, end of the task, end of task. This is at rt. So they say this is a terminal state, s naught, terminal state. Okay, so it's a terminal state, and you get rt there when you go to the terminal state. So this is called an episodic task, task that ends in a terminal state, right? So in this task, what happens? For example, a chess game. I've written it down. So in a chess game, you can keep playing moves, but it will end with a draw, with a white win or a black win, right? Either of the three is going to be a terminal state, right? So just like that, most of the tasks would have a terminal state. There are examples where you want it to exist forever. For example, if you want to control the height of water in a dam, then it does not have a terminal state at all, unless the dam breaks. That's fine. So that is also known as if t tends to infinity, it's called a continuing task. Continuing task. And we'll deal with each of them separately. I don't know why can't you see my screen? Can you see the thing that I wrote?
Yes, visible.
Okay, I hope you can see. I can't see that t tends to infinity. What is happening? So fine. Okay. Okay, now it's visible. Fine. So let us write down. The question asks you to write down a recursion for GT. Can you tell me a recursion for GT? It is very simple, but let's write it down. GT will be written as RT plus 1 plus RT plus 2 R capital T. What is this?
GT minus,
GT plus 1.
sorry, yeah, GT plus.
The rest from T plus 2 to T will be GT plus 1. Therefore, you can write GT as RT plus 1 plus GT plus 1. Fine. So it's again a recursion. So once you get the terminal state, you can do backtracking. So just a computer science algorithm of backtracking would work, or dynamic programming would work. So you start from ST, you go all the way to RT, then you keep adding GT plus RT plus just RT minus 1, or RT, and then you go on GT minus 1 plus RT minus 1, and you continue the loop backwards. So get current GT. That's what the recursion says. Fine. So what happens when the task is not guaranteed to be finite? So what you can show is, if the task is not guaranteed to be not ending in finite time, that is the continuing task, continuing task, say all RTs are finite, RTs are greater than 0, Then do you agree gt equal to summation from t equal to or I equal to 0 to infinity r of t plus I plus 1? This will go to infinity, yes or no? Because all are greater than 0 and there is no convergence here, right? It will diverge, this sum will diverge. Sum of infinite positive numbers. So what people end up doing is they take a discounted reward. That is, you weigh the immediate future more compared to future that is not immediate. That you go distant into the future and those will be having much lower weight. What you end up doing is you define a return function gt as rt plus 1 plus gamma rt plus 2 plus gamma square rt plus 3 and so on. So this becomes gamma to the power I equal to 0 to infinity r of t plus I plus 1. Is this clear to everybody? The method that I'm using? Okay. Any questions? Please don't. If you're not following, please ask. So now I tell you that what is the convergence guarantee of this reward function? What is the guarantee that this reward function will be finite? So we will assume that the rewards RT is bounded by say some B, right? So the maximum you can get a reward is say 10 rupees in a task or anything. So it can't be more than that. So what I can write this as GT can be written as greater less than summation of gamma to the power I B, right? I equal to 0 to infinity. So it's 0 to infinity gamma to the power I. So it's B by 1 by gamma 1 minus gamma, which is less than infinity for all gamma less than 1. Right? Yes or no? Any question? Say rewards are bounded. Okay, if you okay, fine. So we saw an example of a episodic task where say our episode ends every time the chess game ends. So let us take an example of a continuing task without a non-terminal state. Right? Say you have to train a automatic bicycling robot, right? Which has to keep on cycling. So there's this cycle that it has to balance, right? So it has to balance the cycle. And it says that every time it goes out of balance, you give a reward. So out of balance, RT is equal to -1, 0 otherwise. How if out of balance? Okay. This is one of the rewards that I'm just describing to you. So now I tell you at all other steps. So now if I tell you what is the reward function at GT, can you tell me how to do that? Or G0, whatever you say, you start cycling. What is going to be the return at G0? So that is R1 plus R2 dot 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 gamma RT, gamma to the power T RT. First time there was a loss in balance. Let's only consider up to this. Okay, so all of these are 0, right? So G of 0 is gamma to the power T into -1, which is equal to minus gamma to the power T. Fine. So if you have this continuing task going on, so gamma is less than 1. So how will this graph look like? Say if this is your G at a particular time t, and say this is the capital T or whatever the first time for first loss of balance. So do you agree this will look like this?
Yes.
Okay. So it is not exactly going to, as him told, it will look like this. So at t equal to 0, you get -1 as the reward. So what is actually happening is you're decreasing reward, decreasing the penalty. So it incentivizes. What does it incentivize? Can you tell me? This is one of the use cases of discounting with gamma. So you incentivizes longer trails of balance, right? So the more time you take, the less penalty will you receive. So that's the idea. Fine. So we understood what are. So we discussed what are continuing tasks, what are discounted tasks, what is a policy, and so on. So now we have to understand how to decide on best policies or decide what actions to choose. So there comes the first algorithm of a algorithm based on states and event actions. So what we'll try to do is define a function v, which is known as the value function, which will map from states to real numbers. Okay. So what will it give me? It will give me for every state what is the expected reward. Okay. So say you are in ST. So I'll give you an example. Say you are currently in Jadavpur. That is a state of education you are currently in. What is the expected reward that you're going to get? So it's going to be either a very, very high package or you'll go into high, very good or academia positions. So these are the type of expectations you have from a current state you are in. So this is one of the states you will be expectations you get from a particular state. That's what I'm trying to say. So you try to be in those states. The idea is try to reach states that have higher expected rewards. So that's why all the work you're putting in, because you want to reach better states where your chances of getting higher rewards just increases. So you'll just find such examples in real life all around you. Okay. So fine. So what do we define this as? This is the expected reward you are going to expect from a particular state. So it's just going to be this. It's going to be, say, it's the summation over. So RT plus 1 plus gamma RT plus 2 plus dot 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 dot. You're trying to estimate what is this going to be if you are in particular state S. So this is defined as the summation of I equal to 0 to infinity gamma to the power I RT plus I plus 1, given ST is equal to S. Any questions so far? So this is just a definition. So this is called the value function of a state. Remember, value function of a state. That is estimate of how profitable a state can be. Fine. Any questions? Okay. So now the value function or v is very simple. It's just very blunt. So we'll try to make it a bit more spicy, and we'll bring in one more variable. That is, we'll bring in the action over here. So remember, what is our goal? Goal is control again. Control is determining the best action. So if you want to determine the best action, you have to define a function. You have to define a quantify some value with respect to the actions as well. So what people end up doing is they define what is called an action value function or a Q function. Q value function, which defines two things, Q pi. So again, so this, all this here in this case is based on a policy pi. So it's, remember that the policy is fixed here. The policy is fixed here. Because again, if you are trying to wonder what am I saying, so ST, you will be selecting what is the stochastic part in this equation. Can you tell me what is the stochastic, what are the different stochastic elements that you're taking expectation over? First is the pi of, yeah, tell me.
Yeah, so um, the entire policy function is a
Good.
stochastic probability distribution.
So yes, good. Action is chosen based on the policy. Then,
Yes.
so I choose an action A based on the policy. Then I get a reward based on the probability map R from S comma A. Yes or no? Right?
Yes.
And then I go to ST plus 1. That is also based on a probability. That is, you can go from here to here. So just draw this path instead of this as probability of S prime given S comma A. And I just separated out the reward and the states. So these are the different. So R comma S prime is distributed as dot comma dot S comma A. These two are the stochastic distributions that is available, and you will take the expectations over it, over all T's. So we'll come to how to generalize it, but the idea is very clear. You start from a state, take actions based on pi, observe the environment, and just keep adding the rewards, Monte Carlo based. We'll see how to do it mathematically in some time.
Can I ask a question? Uh,
Sure.
can we simplify the expectation
Yeah, you're not
value?
audible.
Yeah, can we simplify the expected value of that summation r to the rt
Hmm.
rt plus I plus 1 given st equal to s using lotus and
Yeah, we can do that. We'll do that. Don't worry.
linearity.
Yeah, we'll do that. We'll simplify it. Don't worry. Just simplifying it is a bit difficult because your RT plus 2 would depend on your subsequent states that you will be receiving. We'll come to that. Don't worry currently about it. Just think about Monte Carlo currently. When we simplify it, you will see the problems generally with just trying to simplify it with Lotus. We'll have to take the entire joint over the entire process. We'll see. It's a good idea. That's what I will do. So a state value function or Q, state action function, Q function, is defined this way. That is the expected reward, again, the expected GT, given ST equal to S. Again, it's a function over the two random variables S and A. Always remember, whichever is the conditioning variable, whichever is the conditioning random variable, conditioning random variable in a conditional expectation, the expectation becomes a function. Expectation becomes a random variable or a function of that random variable. We have discussed it multiple times. Again, here the function, it will become a function of states and actions. Fine. So now, again, same way, I'll write this as expected value summation of I equal to 0 to infinity, gamma to the power I, r to the power I plus t plus 1, given S, T, and AT. Fine. So this is all we are defining this as. This is the, so what does this actually mean? It means given a state and an action A, what is the reward? Reward expected in future. So for example, if you're now a college student and if you take an action of not studying or not doing any, not preparing for anything, you decide what your reward is going to be, something like that. Fine. So it's like the state ST is given, you take an action AT, and what is the reward you are going to expect over all the states, not just one state, till the end of your life, basically. Fine. So now the first question is trying to relate the Q value function and the value function. Let's try to get into this. Fine. So the value function V of S is defined as the expected value of GT given ST is equal to S and AT equal to A. Fine with everybody. So now I'm trying to not sorry, very sorry. This just ST is equal to S, right? So now I'm trying to bring in an action as well. Can you tell me how do I do that? As Antariksh was telling me, we can do it by using a lotus. So say GT be the set of all rewards possible. So GT equal to G over all G's given ST is equal to S. So now what I have to do is I have to introduce what? So remember, the Q function depends both on the state and the action. So but currently I only have the state to me, not the action. So what can I do? Any idea? Again, same logic as you have all told me multiple times before. I will just bring in the action. GT is equal to G, AT is equal to A, ST is equal to S. This is summation over G. I'll just write it in a different way. A in AS, summation over G, G of P of GT equal to G given ST is equal to S, AT equal to A. What will it be multiplied into? Using the trick. So I'm bringing this expectation here. So I will have to multiply it using
Policy.
the policy A given S. So when I'm making this P of, so this is becoming, the action is coming to the conditioning variable. So whatever was previously there in the conditioning variable, which I showed you, will be remaining and the action would be multiplied. So you can clearly see that the inner integral does not depend on the action. So I can just take the action out and I'll get pi of action over S over all actions in the state S. And this function again is the Q function, right? Whatever I have in this the lotus for the Q function. Yes or no? This is summation over G probability of G given S comma A. Fine. So this is just the Q value function over all G. So this is going to be the expected value of, or the Q value of S comma A. This is V pi of S. Clear to everybody? So it's very simple intuitively. So it's like you have a state and action function. Now you sample one action and see what is the value you're going to get. You sample the other action, see what is the value you're going to get, and then take the weighted average. Is this clear to everybody? So this is basically the expected value of Qs comma A, where A is sampled based on the policy. Yes or no? Fine with everybody? So every time you sample an action, you will be choosing what is the Q value of that state and action. You will get the value of that and you will multiply it with the policy, the probability of choosing that action, and you'll get the value of the state. Fine. So here, what becomes crucial is this policy. The policy, if some action is more less likely to be chosen, your value function is not going to be accounted for to choose the state value function. Okay. So now let's come to the most important equation in all of reinforcement learning, or the Bellman equation. That is, we want to prove this equation. We want to find a recursion of V pi. This is the first Bellman equation. We'll do only one Bellman equation today, and we'll see how to generalize it further. So now, how did we relate? We saw V pi in terms of Q pi, right? So now I'm asking you, how can I write Q pi in terms of, the question is how to write Q pi in terms of V pi. Okay, how do I write Q pi in terms of V pi? So I will name the above equation as 1, and then I will see why am I naming this later on. So now, as Antariksh was telling me, to use Lotus, to use linearity and so on, we'll do that. So first, let us define Q pi. What is Q pi of S comma A? Let us first write down the definition. So this is number 2, or rather number 1, 2. Okay, this is number 1. Let us write it down. So Q pi of S comma A. What is the definition? Anyone? The expected reward summation over I equal to 0 to infinity gamma to the power I RT plus I plus 1, given ST is equal to S, AT is equal to A. Fine. So now what can I do? Do you see a recursion over here? I will show you the recursion once. So remember, in the 4 tuple or the MDP, which is the distribution that is just given to you? Which distribution do you only have? The probability of ST plus 1 equal to S prime, RT plus 1 is equal to R, ST is equal to S, AT is equal to A. This is the only distribution that is given to me, not any very large distributions that are required for these expectations, right? So now what I'll try to do is represent everything again in terms of this 4 tuple distribution. Okay, so let us try to do that. First of all, first term I will write RT plus 1 plus gamma times, okay, gamma to the power I RT plus 1 plus I plus 1, given ST is equal to S, AT is equal to A. Is it clear to everybody? Any questions? I equal to 0 to infinity. I just got the T plus 1 out, and I'm writing T plus 2 to infinity here. Okay with everybody? Fine.
Yes.
So now, do you remember what is this? The expected value of P, do you agree, is same as the expected value of P given Q, where this distribution is based on P given Q, and this is just Q. This is how we saw. This is the iterated expectation. First you condition and then take the expectation over that. Remember from your conditional probability, conditional expectation. So I condition based on Q and then I take an expectation based on Q. I took an example where we took a I equal to 1 to n and xi were all Poisson. I told you to find the expected value of this. So n was a geometric. You remember? We choose n equal to n and then xi. And then finally we got then finally we conditioned on n for all values of n. Yes or no? And this was lambda I or something like that. We had taken that example. If the n was also a random variable, we took conditioned n. Okay. So now, can you tell me what do I condition this on? What do I condition on? Which part of this equation I need to condition? Well, using linearity, as Antariksh was telling me, let me write it down first. RT plus 1 given ST equal to S and AT equal to A. Do you agree that this is already known to us? We have derived this. This is the two variable reward function, yes or no? We derived this. The expected reward, expected one step reward, right? If you're not recalling, there you go. Isn't it? This is the function, the expected one step reward, two argument reward. See the definition? Fine.
Yeah, so it's expected two argument. No.
Yeah, expected two argument reward. Perfect. Plus, what do you write? The next part to be gamma times. I'll keep some space. I have already given the hint to you all. Now, do something to make this reward known to me. Can I do something?
Yeah, I can recursively do the same thing again and again, and I
Very good.
kind of get an GP. I mean, not a GP, but kind of.
But I can do this. The recursive thing can be also made simpler. Can I write this as this? As an iterated expectation. St plus 1, sorry. St plus 1 is equal to S prime. Can I write this as this? Right? This is just this entire random variable, which was one expectation. I wrote it in terms of two expectations. Any questions, any doubts? Just forget the conditioning here. Say this is not there. If this is not there, this is true or not. Fine. I just wrote the expected value of P is given to me. You have to find. I just told no, I don't know the expected value of P. What I'll do is I know instead expected value of P given Q. And then I will take expectation with Q. Fine with everybody?
Yes.
So that's what I have done. So I don't know the expectation given ST and A, but I do know the expectation given ST plus 1. Can anyone tell me? Anyone else? How do I know that? Given ST plus 1? What is this? This is just the V pi of S prime, yes or no? Or V prime of ST plus 1, whatever you want. This is the expected reward for state S. The inner one. The expected reward in state ST plus 1. Anyone? Any questions? because this is after this everything is algebra. This is the only step for the Bellman equation derivation. Okay. So I can write this as, I again use linearity to write this as expected reward RT plus 1 plus gamma times V pi of ST plus 1 given ST equal to S, AT equal to A. Clear to everybody? Any questions? I just added both the expectations, this and this. Okay. Great. So now can I use Lotus? If I write down this expectation. So this is your V pi of or Q pi of S comma A. Right? I have written Q pi in terms of V pi. That is the Q value function in terms of the value function. I'm waiting for your response.
Yes, it's okay.
Okay, so can anyone tell me that how to write this down in terms of Lotus?
Expectation of RT plus 1 given ST equal to S, IT equal to A plus gamma into expectation of V pi. I'm just saying the same thing.
Yeah. Okay. Like in terms of summation, can you tell that? Like, say you remember again, this function, everything is known to me. S prime is ST plus 1 is known to me. ST plus 1 is S prime. RT plus 1 is R. ST is equal to S. AT is equal to A. All of these are known to me. This is given by the MDP itself. Yes or no? So
Yeah,
I
so
can,
I'll partition over ST1,
no,
the
no need to
RT
really
plus 1.
partition. You can just write down the Lotus. That is this expectation you're finding, this expectation, right? The expectation of f of x is just, or g of x is just the integral of g of x fx dx. That's all I'm going to do. I'll just sum over all rewards and states and r plus gamma v pi s prime into p of s prime r given s comma a. Is it clear to everybody? So this is your distribution. So this is your st plus 1. This is your rt plus 1. This is your st. This is your at. And this is your st plus 1. Clear? So this is your Bellman equation. So I will just say this is equation 2. Now putting 2 in 1. Remember, let us copy this equation. The number 1 equation. Copy. What will I get? I will get a recursion again. I'll get v pi of s is equal to, I'll just replace the q pi equation over here. Okay. What will I get? A in action of s, pi of a given s, summation over root the rewards, summation over all states, reward plus gamma times v pi of s prime, p of s prime r sa. Clear to everyone? So this is called the Bellman equation. The Bellman equation for a policy pi or policy evaluation. Policy pi or evaluation equation. We'll see another equation next time, which is the optimality equation. But this is the Bellman equation for a policy pi, and it's evaluating how good is it. Is it clear to everybody? Now we'll take an example, it will become clear, but I hope the math was clear. And now I'll try to find out what is V pi. I will show you that you can have a unique solution to V pi. Let's try to find that out. So now the question says that, okay, where is the part of this question? Yeah. So this is the
You just repeat
this
the last two parts, last two
last
steps.
last two steps, as in when I put the V pi, that is clear. When I wrote the recursion as an iterated expectation, like this thing in the on red.
I mean the part after Lotus, using Lotus. That
After
is to
Lotus.
express
Okay.
in terms of policy and that.
Okay, so you mean from q pi to s comma a to how did I write it as a summation? You're saying.
I mean the Lotus part is right. It's okay. I'm asking
Uh-huh.
how did you reach the final Bellman equation, the last penultimate step?
Lotus part is okay. Penultimate step is this is the ultimate step. Penultimate step is you're talking about v pi equal to pi a given s q pi of s given a.
Yeah, the substitution.
You're just putting this is q pi of sa, right? We found out q pi of sa in terms of v pi. Yes or no?
Yeah,
So I just put the value of this equation 2 in equation 1.
yeah,
And when I put that, this is just q pi of s given a, no?
yeah. Oh, all
That's it.
right. Yeah. You just wrote your value function. Yeah,
Yeah,
all right. Yeah, I just
no
didn't
problem.
follow that.
Fine. So now what I'll try to do is I'll try to find a solution to this v pi. There will be a closed form solution if the p's are known. So let us try to understand that. So first of all, we know that we have already found one part of it, that is the reward r sum over all states p s prime r s a over all r summation of a given as pi of a. I'm just expanding distributive property. So the first equation here does not have a state. So I will just integrate state out. So I'll just get p of r given s comma a. Sorry, p of r comma s given a. Sorry, r given s comma a. So now what is this term going to be? Again, we defined this already. Expected reward, two-step reward, two argument reward, right? So this is pi of a in all as, pi of a given s, reward of for a particular state s and an action a. This is v pi of s, right? Plus what else? Summation of a in as. I'll write down the entire thing in distributed property in case you're not following. Gamma times summation of r s prime v pi of s prime ps r s a. So now tell me what I can sum over. Can anyone tell me? I can which variable can I remove from this? I can remove the rewards, yes or no? Fine. Okay. So I'll just rewrite this as a given is pi of a given is plus I'll write down over all S prime. I'm just reordering the summations. S prime summation over rewards and states, rewards and actions, sorry, pi of A given S, P S prime R S A. Do you recall this equation? This inner equation? We have already derived this once. I'll show you what we had derived. There you go. Yes or no? We have derived this. This is the transition probability from state S to state S prime. Given a policy, yes or no?
Yeah.
So I will just replace that as a transition probability, just simplifying stuff. So this is the probability of S prime given S. Look at the beginning. Okay. So now this equation, can anyone tell me what is it? I can further reduce it to the expected reward of a state because I'm averaging across all actions, yes or no? Fine. Because this is the expected value over all actions. A will just be removed, yes or no? Just S is given, so S will just stay because you're summing over all actions, yes or no? This is the average value over all actions. So this is the expected reward, expected one argument reward. There is no action term over here. And then the second term, do you agree, is V pi of S prime, probability of S prime given S over all S prime. Now, can anyone write this as a vector notation? So if I write this as P matrix P S prime S as 1 1 1 2 dot 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 1 n, where P1n is probability of S prime is equal to n and S is equal to 1. Can anyone tell me what will I write this as? Transition from transition, we did it last day, from state I to J. So do you agree? This is the, so if I write for all S, can I write V pi is equal to R pi plus this matrix P? There's a gamma as well. I forgot the gamma, sorry. P into V pi. Do you agree? So because this is just for every S, I am taking a summation over linear combination of all other V pi 1 and so on. So this is my equation. This is called the Bellman operator equation, where the Bellman operator is, or Bellman operator T pi, this is called the Bellman operator is equal to R pi plus gamma P. Okay, where P, again P here again depends on the policy, so you can write P pi as well on the top. So gamma R pi, the one-step reward function, plus gamma P pi. So this is the Bellman optimality equation. Therefore, this equation shows like you can write this in a compressed form as this, in an operator sense, in an operator equation. So where only this takes the input, V pi into V, right? So now if I ask you what is the solution to V pi, can anyone tell me if all of these values are known? V pi is identity minus gamma P pi is equal to R pi. So V pi is I minus gamma p pi inverse r pi, if the inverse exists. Clear to everyone? I'll wait for a moment before I go to the example. Any questions? Please go over this, solve it yourself. So I've gone over the entire Bellman operator. Once you understand this, you give me a feedback, I can talk about its convergence. Otherwise, talking about its convergence is not a good idea. We'll talk about the algorithm next day. But this is the Bellman equation and the Bellman operator. Fine. So this part is the Bellman operator. Fine. It's a linear operator, as you can clearly see. It's just a linear summation. Okay. I hope there's no, if there are no questions, I'll do a simple example again from Saturn and Barto. And I'll stop today. So what does this example say? It's a grid world example. What does grid world mean? So these are the states. So it's given that these are the states. And you have actions of up, down, left, and right. So it's very intuitive setting. Say if you are here, you go up here, right, left here, right here, and down respectively, right? And you are told that the policy pi, that is up given state, is equal to left given s, and for all s is equal to 1/4. That you have a uniform policy for all states is given to you. Fine. That is, at every state you are equally likely to move in any other boxes. What it says that if you go out of a box, you return to the box, and there are two special states, that is state A and state A prime. Fine. So as soon as you go to state A, it says that you go to state A prime. There is no, every action you choose in A, it always takes you to A prime with a reward of +10. And every other state, any action you choose, you get a reward of -1. Is this clear to everyone? I know if you go out of the grid is -1, else any action you choose, you get a reward of 0. Any question? So once you get to this state, you jump to A prime. Once you get to B, you go jump to B prime. Okay. So now your homework would be this. Please try to do for B to state B, what is the V pi of B and V pi of this. So what I'll try to do is here, I'll try to verify the Bellman equation. So let us try to verify the Bellman equation. What is the Bellman equation again? For a state, actions in the state, pi of A given S, summation over R, summation over S prime, R plus gamma, V pi of S prime, P of S prime, R S A. Fine. This is my equation. Now I am told to find V pi of 1 equal to question mark. Now tell me, what is the action that I have here? What is the only action that I have in state 1? Any action I choose, where will I end up going? Only action available in 1 is to, or in A, is to go to A prime. Yes or no? Any questions? Okay. So,
Could you show the grid again?
okay. You want to see the grid again? I'll draw the grid here. No worries. The 5x5 grid. This is the grid. From this state, it always goes to this state. And from this state, it always goes to this state. Reward is +10, reward is +5. Okay. So now I'm asking you, if you are in state A to state A prime, what is the only action you can choose from A8 is to go to A prime. Yes or no? There is
Yeah.
no other option. No other option. Therefore, v pi of action A, this is just going to be any action. Just go to A prime given S is just going to be probability 1. So therefore, all other actions does not need to be considered at all. So the inner summation, what will it be? So if there is no variability in reward because reward is just, what is the reward value? 10. Yes or no? Fine. And what is S prime? A prime. Do you agree? Fine. So therefore, probability of A prime 10 given A and whatever action you choose, small a is just 1. Rest all the probabilities are going to be 0. So therefore, can you tell me what is this going to be the value? It will be just 10 plus, say gamma is chosen to be, I think, 0.9. 0.9. 0.9. 0.9 into.
Minus
So
1.0.
yes, minus 1.3, which is, let me take the calculator. See the 0.9 into 1.3 minus 10. This is my 8.83. Right? This is how you calculate this. Now, if you've understood this, let's take the last example. So state 2, v pi of 2. Now, anyone else, can you help me with this? So I have verified this. This is indeed 8.8. So yes, correct. So now let's check for v pi of 2. Anyone?
So in v pi of 2, we have only two possible actions, right?
No,
Which
you
column?
have all actions actually. So I told you that if you go up, you go up, you go left, you go left. The right and the left, you will just fall back to itself. And you'll get a reward of -1. And you'll get a reward of 0. Yeah. Okay. Tell me now. So what are the 4 actions? Up, down, left, right. So for up, 1/4 is the probability. So this is for up. Pi of up given 2 is equal to 1/4. Pi of down given 2 is equal to 1/4. Pi of left, or rather not down, sorry, left, right given 2 equal to pi of left down given 2 is equal to 1/4. So now tell me, do you agree that right and the down can be clubbed together as a single action? Because it
Yeah.
returns to the same state. So we can write this as out of grid given state 2. This is probability half. Do you agree? Because one of the two times it will go out. Fine, just adding both of them. So now 1/4 is the probability. I will write something down over here. 1/4 is the probability. I'll write down something here. And half is the probability for growing out of the grid. Okay. So now the inner summation in the Bellman equation, what will it turn out to be? There is no stochasticity here, right? So you're just going to one state. Can you tell me the inner summation, the inner value?
For the first 1/4, it would be
Okay.
gamma into minus 1.4. Sorry,
Okay. Point.
I was talking about the left one. So
Okay. 1.4. Very good.
yeah, minus 1.4.
This is for the left. For the up, anyone else? Feel free, no worries. So if you go up, you will get a reward of 0. You have the state value is 1.2 and this is 0.9. That's it. And for the outgoing cell, reward is -1 and you return to the same state. That is 0.9 into 2. Right? So just if you write it down, so you'll get 1/4 minus 0.9 into 1.4 2.6, right? 2.6, 0.9 into 2.6 minus half into 2.8, 1.4, 1.3, 0.9 into 0.65 minus 1.4, 0.9 into 0.65 minus 1.4, that is 1.985, 1.99. Again, that matches with our value, approximate value of -2, sorry. Fine, any questions? Please go back and try to find out for 3-4 other grids. Homework is find for 3 or 4 other states. That is very fine, not find. We'll continue from here from the next day. So any questions? We have completed what we intended to go today, but yeah. Any questions you want me to take? Okay. So we did the first Bellman evaluation equation today. We'll do the Bellman optimality equation the next time on Wednesday, probably. If you have no further questions, I'll stop recording. Okay, now any questions?